Welcome to the deep dive. We cut through the noise, get straight to the core, all tailored just for you. Today, we're doing something really captivating. We're diving into the world of helicopters. You know, these incredible machines, they seem to defy gravity, soar through the air. It looks like magic, really, with those rotary wings. So our mission today is to unpack the core principles, the details behind helicopter aerodynamics, structures, and systems. We're pulling insights from key texts like the Helicopter Aerodynamic Structures and Systems, EA's Part 66 Module 12 series. So if you're maybe an aspiring aircraft maintenance engineer looking for that essential knowledge, or maybe you're a seasoned aviation enthusiast just wanting more, or even just curious about what keeps these amazing machines safely flying, well, this deep dive is definitely for you.
That's absolutely right. We want to give you a kind of shortcut to being really well informed here. We're focusing on the practical stuff, the surprising facts, and maybe those moments that stick with you. We'll look at everything from, the basic forces lifting the helicopter off the ground to the really intricate systems keeping it all running smoothly. Think of it as a solid overview of the world an aviation maintenance engineer works in every day. It really gives you insight into the precision, the dedication needed for these complex machines.
Okay, great. Let's start unpacking this. Helicopters. They fall under the banner of rotorcraft, right? An aircraft using a rotating wing for lift. But it's not just one type, is it? There are nuances. What are the key differences we should know?
Yeah, good point. While a helicopter, like the ones we're mostly talking about, uses its engine-driven main rotor for both lift and pushing it horizontally. There are other types. You've got gyroplanes, for instance. Their main rotor isn't powered by the engine. It just windmills, essentially, as air flows over it. They need a separate propeller for forward flight.
Okay, so autorotation provides the lift, but something else pushes it forward.
Exactly. And then there are gyrodynes. They do have an engine-driven main rotor, mostly for lift, but they also use a conventional propeller or maybe turbine thrust for forward movement.
Got it. So when we say helicopter, we mean that classic design engine drives the main rotor for both lift and direction.
Precisely. That iconic setup.
So those blades, it's clearly not just simple spinning. There's some serious physics at play up there. Let's get into blade dynamics. What happens with the main rotor blades when the helicopter actually starts moving forward? It can't be straightforward.
No, not at all. And this is fundamental. We need to talk about advancing versus retreating blades. When a helicopter flies forward, the blade rotating into the direction of flight. That's the advancing blade.
Yeah.
Its speed relative to the oncoming air actually increases.
Okay, so it's going faster through the air.
Right. But the blade on the other side, rotating away from the direction of flight, that's the retreating blade, and its speed relative to the air decreases.
Can you give us some numbers? Make it a bit more concrete.
Sure. Let's say the blade tip speed, just from rotation, is 400 knots, and the helicopter itself is moving forward at 100 knots.
Okay.
The tip of that advancing blade is now experiencing airflow at 500 knots. That's the 400 plus the 100.
Right, makes sense.
But the retreating blade tip, it's only seeing 300 knots of airflow. That's 400 minus the 100.
Wow, that's a huge difference across the rotor disc, 500 versus 300 knots.
Exactly. And the speed differential, it's absolutely critical. It creates major challenges.
Critical how? What kind of problems or dangers even does that create?
Well, this is where things get complex and potentially hazardous if not managed. This difference in airspeed leads directly to unequal lift. More speed generally means more lift.
So the advancing blade wants to lift more than the retreating blade.
Precisely. Yeah, and that imbalance has to be corrected. But there's another issue. Retreating blade stall. Because the inner parts of any blade rotate slower than the tips. On that retreating side, those inner sections, already moving slower relative to the air, can lose lift first. They stall.
Stall meaning they stop generating lift effectively.
Correct. And in some conditions, the helicopter's forward speed can actually cancel out the aft rotational speed of a section of the retreating blade. So that part has effectively zero airflow over it.
Uh-oh.
Yeah. This forces the outer part of the retreating blade to work much harder, increasing its angle of attack to compensate. That high angle of attack near the tip can then cause the tip itself to stall, hence blade tip stall. It's a major limiting factor for helicopter speed.
Okay, that's a huge constraint. What about other forces? Centrifugal force must be massive too.
Oh, absolutely immense. Centrifugal force is what throws the blades outward from the hub, keeping them stiff and straight in flight. It's determined by the RPM and the rotor diameter. The faster it spins, the bigger the rotor, the greater the force. It's essential for keeping the blades rigid against the aerodynamic forces trying to bend them.
Right. Okay, so complex blade dynamics. Then there's this other concept, the Coriolis effect. You often hear the figure skater analogy. What is that, and why is it so vital for helicopter rotors?
Ah, the Coriolis effect. It's basically the law of conservation of angular momentum in action. And that figure skater example, it's perfect. Skaters start spinning, arms and leg out wide, spinning relatively slowly.
Yeah.
Then they pull their arms and leg in tight towards their body. What happens?
They spin much, much faster.
Exactly. Because their mass is now closer to the axis of rotation, their moment of inertia decreases.
Yeah.
To keep angular momentum the same, since no external torque is applied, their angular velocity has to increase. They speed up.
Okay, I see the physics. How does that apply to a rotor blade flapping up and down?
Well, as a blade flaps up, its center of mass moves slightly closer to the rotor hub, the center of rotation. Just like the skater pulling their arms in, the blade naturally wants to speed up in its rotation.
Ah. Okay.
And when it flaps down, its center of mass moves slightly further out. Like the skater extending their arms, it naturally wants to slow down.
So the blades are constantly trying to speed up and slow down as they flap.
Constantly. And these accelerations and decelerations create tremendous stresses known as Coriolis forces, especially at the blade root and in the hub. This is a huge deal for engineers. You need ways to accommodate this. That's why early helicopters had lead-lag hinges.
To let the blades move slightly forward and backward in the plane of rotation.
Precisely. To absorb those Coriolis forces. Without hinges or flexible blade designs, the stresses could literally tear the rotor head apart. So it's not just a neat physics trick. It fundamentally drives the engineering design of the rotor system.
That's fascinating. Physics dictating complex engineering. Okay, so pilots need to manage all this. Let's talk controls. How does a pilot actually command the helicopter? What are the primary controls?
Okay, the main control for directing the helicopter's movement forward, back, sideways is the cyclic stick. Usually the one between the pilot's legs.
And how does that work mechanically?
It manipulates something called the swash plate. This is a really clever mechanism around the main rotor mast. It's basically two rings, one rotating with the mast, one stationary. Tilting the stationary ring tilts the rotating one, which then changes the pitch angle of each individual main rotor blade as it goes around its cycle.
So tilting the stick forward makes the blades have more pitch on the backside and less on the front, tilting the whole rotor thrust forward.
Essentially, yes. It introduces a cyclical change in pitch, tilting the overall rotor disc and directing the thrust, which moves the helicopter.
Clever. And the tail rotor. What's its specific job? People often get this wrong, don't they?
They do. The tail rotor's not for steering the direction of flight. That's the cyclic's job. The tail rotor's primary purpose is to counteract the torque from the main rotor.
The tendency for the fuselage to spin in the opposite direction to the main blades.
Exactly. And by changing the thrust of the tail rotor, using the anti-torque pedals, the pilot controls the helicopter's heading. It's yaw. Left pedal makes the nose go left, right pedal makes it go right.
Okay, heading control, not direction control.
I do.
And do tail rotors also have issues with advancing retreating blades?
They do, but it's usually less pronounced because they're smaller and operate in less disturbed air, generally. They often have flapping hinges too, allowing the blades to flap and automatically adjust their pitch slightly as they advance and retreat, smoothing out the thrust.
Right. These engineering solutions are really something. Let's dig into the rotor systems themselves. You mentioned hinges earlier. Traditional designs are often called fully articulated. What does that actually mean?
Fully articulated means each blade is attached to the hub with a set of hinges, typically three kinds. A flapping hinge allows the blade to move up and down. A lead lag or drag hinge allows it to move slightly forward and backward in the plane of rotation, managing those Coriolis forces we talked about.
Okay.
And a pitch change hinge allows the blade's angle of attack to be changed by the control system. So each blade has quite a lot of freedom to move independently. This was crucial for managing the complex forces on early helicopter designs.
But it sounds mechanically complex. Lots of moving parts, bearings, maintenance.
Definitely. Very complex, heavy, and maintenance intensive, which is why modern designs often move towards simpler systems.
Like the hingeless or rigid rotor systems I've heard about?
Exactly. Well, rigid is a bit of a misnomer. They still flex. But hingeless is more accurate. Designs like the one on the Eurocopter, BK-117 or EC-145, use advanced composite blades. These blades, often glass or carbon fiber reinforced plastics, have flexibility engineered right into the blade root or the flex beam.
Ah, so the material itself bends and twists to accommodate the flapping and lead lag motions.
Precisely. It eliminates many of the mechanical hinges, simplifying the rotor head, reducing weight and maintenance. It's a big leap forward.
And attaching these blades, whether hinged or hingeless, must require incredibly strong methods given the forces involved.
Absolutely critical. Common methods include using a blade grip that clamps around the blade root, like on a Bell 206, or blade spindles, or bolted blade flanges. The engineering has to be flawless.
You mentioned those forces earlier. Can you remind us of that example? It was staggering.
Yeah, the Sikorsky SH-60 blade example. The blade itself weighs maybe 113 kilograms, around 250 pounds. But at normal operating RPM, the centrifugal force pulling it outwards is about 450 Gs.
450 times the force of gravity.
Yes, which means that 250-pound blade feels like it weighs, well, do the math, over 50,000 kilograms or 112,500 pounds. That's the force the blade root and the hub attachments have to withstand constantly.
That's just incredible. Okay, so that massive main rotor torque needs countering. You mentioned the tail rotor. Are there other ways, more innovative anti-torque solutions?
Yes, definitely. One well-known example is the Fenestron, often seen on Eurocopter, now Airbus helicopters.
That's the fan and tail design, right? Enclosed in the tail boom.
Exactly. It's essentially a multi-bladed ducted fan, usually 8 to 18 small airfoil-shaped blades housed inside a protective shroud or tunnel. This enclosure offers protection, reduces noise, and improves aerodynamic efficiency compared to an open tail rotor. Because the blades are smaller and shrouded, they often don't need flapping or drag hinges, which simplifies the design again.
Interesting. Any other concepts?
There's the NOTAR system, which stands for NO tail rotor. You see this on some MD helicopters like the MD-500 series.
No tail rotor at all. How does that work?
It uses a variable pitch fan inside the fuselage near the back. This fan blows low-pressure, high-volume air down the tail boom. Some of this air exits through controllable slots along one side of the boom, creating an aerodynamic effect called the Coulomb effect, which generates sideways lift, countering the main rotor torque. Additional air is expelled through a controllable nozzle at the very end for yaw control.
Wow, using airflow itself.
Yeah.
And you mentioned a manufacturing improvement there.
Yeah, quite impressive. For the NOTAR fan blades, newer manufacturing techniques brought production time down from about 10 hours per blade, with a 20% scrap rate for the older composite methods, down to just 5 minutes per blade with only a 3% scrap rate. That's a huge efficiency gain for production and maintenance supply.
That really highlights the continuous innovation. Okay, moving from force generation to force control, hydraulic systems. Especially on larger helicopters, these must be absolutely critical, right? Why the need for redundancy?
Oh, absolutely vital. The control forces required to move the swash plate or tail rotor pitch mechanisms on larger helicopters are immense, far too much for a pilot to handle directly through mechanical linkages alone. So hydraulic systems provide the muscle. And redundancy is key for safety. Heavy helicopters will typically have at least 2 completely separate hydraulic circuits, 2 reservoirs, multiple engine-driven or electrically driven pumps, powering critical systems like the main and tail rotor servo controls, maybe landing gear too.
So if one system leaks or a pump fails,
The other system can maintain control. It's a fundamental safety requirement. Lose hydraulic power to the main rotor controls and you likely lose the aircraft.
makes sense. And technology is changing how these are controlled too. Less mechanical linkage.
Yes, we're seeing more fly-by-wire influence. Pilot stick movements generate electrical signals, which then command electrohydraulic actuators to move the flight controls. This can save weight and complexity compared to long mechanical rods and bell cranks.
But doesn't that remove the pilot's feel of the control forces?
It can, yes. These systems are often non-reversible, meaning aerodynamic forces on the control surfaces don't feed back to the pilot's stick. So systems often incorporate artificial feel mechanisms, springs, bungee cords, or even small hydraulic actuators to simulate those aerodynamic loads and give the pilot tactile feedback.
Okay, fascinating. Let's shift to keeping things smooth. Vibrations are a big deal in helicopters. What causes them and how are they managed?
Vibrations are inherent, unfortunately. They can come from basically any rotating component. The engines, gearboxes, drive shafts, tail rotors, and of course the main rotor. The main rotor is usually the biggest culprit due to its size and the complex aerodynamics.
So how do maintenance engineers tackle this? Blade tracking and balancing.
Exactly. Balancing is crucial. There's static balancing, which is about ensuring the weight distribution along the length of the blade is correct, usually done by adding or removing small weights at the blade tip. Then there's dynamic balancing, which addresses imbalances that might cause wobbling or vibration as the rotor spins, looking at the balance across the rotor disc.
And Aerodynamic balancing. You mentioned tabs.
Right. Even if blades weigh the same and are balanced statically and dynamically, slight differences in their shape or twist can make them produce slightly different amounts of lift at the same pitch angle. To fix this, many blades have small, bendable metal tabs on their trailing edges. Mechanics can carefully bend these tabs up or down to slightly change the blade's lift characteristics, fine-tuning it to match the others and reduce vibration.
And blade tracking. How do they actually see if the blades are flying in the same plane?
Yeah, this is pretty cool for an AME student to see. The goal is to ensure all blade tips are following the same path as they rotate. An older method used a sort of flag on a pole, carefully brought up towards the rotor disc to mark the path at each blade tip with chalk or grease pencil. Very hands-on.
Sounds a bit hazardous.
It could be. A more modern and common method uses strobe lighting. Reflective markers, maybe different shapes like a triangle, square, circle, diamond for a four-blade system, are put on or under the blade tips. Then during a ground run, or even in flight, a mechanic uses a strobe light synchronized to the rotor's RPM, aimed up at the rotor disc. Because of the strobe effect, the reflected targets appear to stand still, or move very slowly.
Ah, so you can visually see if one blade tip is flying higher or lower than the others?
Exactly. You can see the vertical separation between the tips. Then you make adjustments, usually to the pitch links connecting the swash plate to the blades, to bring them all into the same track. It requires incredible precision.
That strobe method sounds much safer and more precise. Okay, from dynamics to the static structure, the airframe itself. How are structures classified in terms of importance? This must guide maintenance decisions, right?
Absolutely. Structures are typically classified into three categories. Primary structure. These are parts where failure would likely cause catastrophic loss of the aircraft. Think main rotor mass, critical spars, main fuselage frames. Damage here is extremely serious.
Hey, top priority.
Secondary structure. These are significantly stressed parts, but their failure wouldn't necessarily cause immediate loss. Maybe certain skin panels, floor beams, less critical ribs. Damage needs careful assessment and repair, but might not ground the aircraft instantly. Tertiary structure. These are lightly stressed parts, often things like fairings, brackets, access panels. Their failure is generally not a safety of flight issue, more about aerodynamics or protecting components.
So for an AME, knowing if a crack is in a primary or tertiary structure completely changes the response.
Completely. Primary structure damage demands immediate attention, often replacement or highly specialized repair procedures. Tertiary damage might just be noted for later repair. It dictates the urgency and the repair standards.
That makes sense. And what about the underlying design philosophies for safety? Fail-safe versus safe life.
Two key approaches. Fail-safe design assumes that parts will eventually fail or crack, so the structure is designed with redundancy. It might have multiple load paths, so if one part breaks, another can carry the load. It also includes features to slow down crack growth, like crack arresters, often straps riveted across potential crack paths, and emphasizes inspectability so damage can be found early.
Building in tolerance for failure.
Right. Safe life, on the other hand, is based on calculating a component's expected fatigue life. Components designed this way, like maybe landing gear components or certain rotating parts, are assumed to be safe for a specific number of flight hours or cycles. They are then mandatorily removed from service and replaced when they reach that life limit, before they are expected to fail due to fatigue, even if they look perfectly fine.
Proactive replacement based on calculated life.
Exactly. Many aircraft use a mix of both philosophies, depending on the component.
And stress itself. What are the main types AMEs need to understand?
The classics: tension pulling, compression squashing, shear sliding action like scissors, torsion, twisting, and bending, a combination of tension and compression. Helicopter rotor blades experience significant bending loads as they flap. Drive shafts experience torsion. Fuselage structures see complex combinations.
Any types of stress less relevant to helicopters?
Well, hoop stress, which is caused by internal pressure trying to burst a cylinder, isn't usually a major concern for the fuselage structure itself, unlike high-altitude pressurized airliners. Helicopters typically fly lower and aren't pressurized to the same extent.
Got it. And metal fatigue, that's the hidden danger, right?
It really is. Repeated loading and unloading, even if the stress is well below the material's ultimate strength, can cause microscopic cracks to form and grow over time. This is why regular detailed inspections, especially in known high-stress areas, are absolutely critical for an AME. Finding these tiny fatigue cracks before they become critical is paramount.
Okay, so how are these airframes actually built? What are the common construction techniques?
Most modern helicopters use stressed skin construction, usually semi-monocoque. This means the outer skin carries a significant portion of the flight loads, working together with an internal framework.
And that framework consists of?
Things like bulkheads, which are like structural walls across the fuselage to maintain its shape longerons, which are the main lengthwise structural members, and stringers, which are smaller lengthwise stiffeners running between the longerons and bulkheads to support the skin and prevent buckling.
So the skin and framework together, how are they joined?
Primarily through riveting, that's very common. Also bolting, especially for high-load connections. You might see specialized bolts like Hylocks, which provide very high strength and vibration resistance, and increasingly bonding using high-strength adhesives, sometimes in combination with rivets or bolts, a technique called riv bonding. Bonding can produce smooth surfaces and distribute loads well.
Building it is one thing, protecting it is another. Corrosion seems like a constant battle.
It is, especially with metal structures operating in varied environments. Prevention is multi-layered. It starts with material selection using corrosion-resistant alloys where possible. Then, proper heat treatments are important. After that, surface treatments are key. Chemical conversion coatings like chromating or anodizing for aluminum alloys, followed by primers and paint layers.
So multiple barriers.
Yes, and ongoing maintenance is vital. Regular cleaning to remove corrosive agents like salt or dirt, making sure drain holes are clear so water doesn't get trapped. Applying corrosion-inhibiting compounds. It's a continuous effort.
And keeping everything aligned. Symmetry must be crucial.
Extremely. Precise alignment is checked during manufacture and after any major repairs. Misalignment can induce stresses or affect flight characteristics. Technicians might use jigs, optical alignment tools, or even methods like dropping plumb bobs and drawing center lines on the hangar floor to check and ensure the airframe's symmetry and alignment are within strict tolerances. For an AME, ensuring this symmetry is part of maintaining the aircraft's integrity.
Right, meticulous work. Okay, let's move inside to the veins and nerves, the electrical systems. What powers these machines? Battery types.
Okay, electrical power. You'll typically find batteries for starting and emergency power. Common types are the traditional lead-acid, nickel-cadmium, or NiCd, and increasingly lithium-ion, Li-ion. NiCds have been workhorses for years, good power density but can suffer memory effect. Li-ion offers better energy density but requires more complex monitoring and safety systems due to thermal runaway risks. They use a water-free electrolyte, which is a key difference.
And power generation when the engines are running?
Primarily from engine-driven generators, which usually produce DC power directly, or alternators, which produce AC power. Helicopter AC power is often 115 volts at 400 Hz. Keeping that frequency stable as engine RPM changes requires a constant speed drive, CSD, or similar integrated drive generator systems.
So you have DC from batteries and generators, AC from alternators. How is it all managed and converted?
Through various distribution buses and components. If you need AC from DC, you use an inverter. If you need to change AC voltage, you use a transformer. And very commonly, you need DC power from the AC generators. So you use rectifiers, transformer rectifier units, or TRUs, to convert AC to DC.
Okay, lots of conversion happening. And protection.
It's essential. You have fuses and circuit breakers distributed throughout the system to protect wiring and components from overcurrents and short circuits, a fundamental safety aspect an AME constantly interacts with.
Makes sense. And this leads us to the really smart aspects, onboard maintenance and information systems. How do modern helicopters help diagnose themselves?
They're getting very sophisticated. Many have central maintenance computers, CMCs. These computers constantly monitor data from various aircraft systems, engines, hydraulics, avionics, looking for faults or exceedances. They can then record these faults and display messages to the flight crew or maintenance personnel, often prioritizing them by severity.
So it points the mechanic in the right direction.
Exactly. And it goes further with built-in test equipment. BITE. Many individual components called line replaceable units, LRUs, things like flight control computers, radios, display units, have their own internal BITE circuits. When commanded, or sometimes continuously, these circuits run self-tests on the LRU's functions. They often report the status with simple indicators, maybe a green light for good, red for fault, or they send detailed status reports to the CMC. This drastically speeds up troubleshooting for AMEs. Instead of testing a whole system, BITE might say, LRU number 3 has an internal fault. Swap the box.
Very efficient. What about monitoring the structure itself electronically?
Yes, that's advancing too. For fatigue-critical structures, FCS, beyond the scheduled damage tolerance inspections, DTIs, some aircraft are incorporating strain sensors. These are small devices bonded to critical structural locations. They measure the actual strain or deformation in the structure by detecting tiny changes in electrical resistance as the material stretches or compresses.
So you get real-time data on structural stress.
Potentially, yes, or accumulated fatigue data. It's part of Health and Usage Monitoring Systems, HUMS, aiming to detect problems before they become critical based on actual usage, not just scheduled inspections. This is really relevant for students to understand the future of structural maintenance.
And the paperwork, or lack thereof. Electronic systems are changing that too.
Big time. The Electronic Flight Bag, EFB, for pilots is replacing heavy bags of paper charts and manuals with tablets containing all that data, easily updated. And for maintenance, electronic logbooks are becoming more common, recording maintenance actions, component histories, tracking flight hours digitally. It improves accuracy, accessibility, and efficiency compared to traditional paper logs. For future AMEs, being comfortable with these digital tools is becoming essential.
And passengers get connectivity too.
Yeah, things like wireless media streamers and special leaky line antennas running through the cabin allow passengers to connect their devices, though that's more about comfort than core aircraft maintenance.
Right. Well, it's truly incredible when you pull back and see all the layers. The aerodynamics, the structures, the controls, the systems, all working in concert.
It really is. And it underlines something important. Despite all the amazing tech, the composite blades, the fly-by-wire potential, the smart diagnostics, the human element, especially the skilled aviation maintenance engineer, remains absolutely central to it all. Your understanding, your hands-on skills, interpreting the data, making those fine adjustments, ensuring the physical integrity, that expertise is irreplaceable for safety and efficiency. The tech helps, but the human makes the final call.
A perfect summary. So the next time you see a helicopter, maybe hovering seemingly effortlessly or taking off with that unique grace, think beyond just the spinning blades. Consider that hidden symphony of complex, meticulously engineered systems and the skill and dedication of the human hands that ensure they all work in perfect harmony. It makes you wonder, doesn't it? What other complex system in your daily life, something that seems almost effortless on the surface, might have its own fascinating deep dive just waiting to be uncovered?